Hello and welcome to Precision Stuff. Today, this is going to be a little bit different. This is actually more of a podcast. I'm giving something new a try. These are a few of my thoughts and feelings on the engineering process, how to actually accomplish good engineering at work, and how to avoid architectural churn and make sure your project is not a boondoggle. It's a little bit like a manifesto or maybe a list of hard lessons learned about how to find out when a problem is difficult, how to solve problems in the right order, and what to worry about. The only thing that matters is programmatic risk. You don't want your project to be the boondoggle project. The boondoggle project is the one that gets passed between multiple people. Those people often leave the company or they get exited. It doesn't show up on time. It doesn't work. It's expensive. It's late. The vendor is difficult. It breaks in the field. It doesn't meet requirements. And it's like a constant burning fire for engineering and reliability and supply chain. It's that project. You don't want to be that project. So the goal is not avoid programmatic risk. You have to be careful and calculated about your programmatic risk budget. If you take no chances, no risk, you're probably not going to be able to improve your performance that much in the system. So what does it mean to be careful about programmatic risk? One, you got to be really, really good about requirements. A lot of ways projects turn into boondoggles is they miss the key requirement. And essentially, first you have stakeholders, then you have requirements, then you have architecture, then you have initial design, then you have detailed design, and then you have like your stuff in the field at rate mature, and you're ramping. So the biggest problems are the ones that like someone made a mistake very early on in the process when it was fixable, and then it just carried through. If you just missed a stakeholder, for example, let's say you knew that your part had electrical, thermal, and mechanical needs, but you just missed that there was like an aero detail. Like actually, it is part of the OML, and you never talked to the aero people about it, and like you put some giant heat sink fin in the airstream, and they don't like that for drag reasons. It's going to blow up the wing. That's where you could have a perfect design that meets 3 out of 4 requirements. Because it missed the 4th, it has to be entirely scrapped and redone. Something to avoid here is architectural churn. Architectural churn happens when you don't have the right requirements, usually because you're missing one, or one of the requirements is not as important, like the weighing of the requirements was not done correctly. Like something was considered a P1 when it's really a P0. Those are the things that blow up programs. So stakeholders, you got to know who actually cares about the outcome here. It's like you're not just making it for yourself, you're making it for a lot of people. So at the beginning of the project, it's really good to do anthropology, which you talk to all the stakeholders. And it's in engineering, it's in design, it's in reliability, it's in testing, it's in supply chain, it's in SIE. It's like everybody, maintenance, manufacturing, anyone who's going to touch this part, talk to them. Figure out what they know, what they like, what they care about, what they hate about the existing design. One of the things people often miss is like they write down the technical requirements, but they miss the programmatic requirements, which is, oh, my part goes on the plane early, so it needs to show up earlier compared to other people's parts because other people's parts bolt onto me, which means that your maturity level needs to be leading that of your interfaces. Like you actually have to be a few weeks ahead of the rest of the program, otherwise you're going to be throwing a bunch of churn and burn into your colleagues' designs. So that's especially true for interfaces, which have to be dealt with early. Like anytime you owe something to a different department, that has to be a higher priority than something that just lives within you. If you have a complex interface on the vehicle, if you want to change that interface, it's going to crash through a million different departments. It takes a huge coordinated effort. Be really, really careful. You have to lock that kind of stuff early. It's like an ice cube freezing from the bottom up or something. The maturity grows from the base outwards, or in this case, from interfaces outwards. If you have a multi-department, multidisciplinary interface, you got to lock that first because that's the highest risk for churn and burn. And then when it comes to the little 1 millimeter deep inside of your box that only you are ever going to know about, you could leave that to the last. You could almost get to like gross negligence on those internal details as long as you are confident that they're not going to be architecturally damaging if you get them wrong. This is probably the most important saying. It's okay to be wrong if you're wrong fast. If you're slow, you have to be right slowly. And this is 2 methods of thought. If your part, let's say your part is literally just a machine block of aluminum with holes in it, you can design it probably pretty quickly, and you might be able to get it made in, days to weeks, depending on vendors and availability, which means you can make it, look at it, be like, oh, wow, the hole's in the wrong place. I screwed it up. I need to move it over a little bit. And then you could go buy it again, and you could buy it again, you could buy it again. And basically, because your iteration time is maybe 1, 2, 3 weeks, you can go through that process so fast. You can afford to be lazy, you can afford to be wrong, you can afford to miss requirements, and you're not going to create a boondoggle. The other extreme is If you're working on long lead, high complexity, high capex cost tooling, you got to be right the first time because it's very slow iteration. It's very expensive. Slow begets slow. Like primary structure, it just takes weeks to go make the tooling and get parts, which means you have to be right, which means you have to be right very early, which means you have to do all this work up front, which means you need to have a really polished crystal ball that allows you to look into the future. You need to make good decisions months in advance of when you're going to know if they're good or not. That's like just wisdom and experience. It's really hard. And you probably need to have really big checklists of, I need to be worried about these 10 things in order. And inside of every one of those things, there's 10 little details I need to go check. And you have to be really thorough about making sure that you've imagined every possible thing that can go wrong, check against them, get someone to confirm that you actually did it right. So the amount of design work up front is way higher because the amount of time and money you're going to spend making that part is tremendously high. So if you could, you'd always prefer to have a fast, high iteration process that allows you to churn and burn through bad ideas quickly, move fast, make mistakes, get to the right part. Basically, your goal in life is always get to version like 3 as fast as you can. And it turns out making version 1, version 2 being like really bad but fast is actually a great way to get to version 3 quickly because you just learn so fast once you have the hardware in hand. There's some things that you're going to learn from having the hardware in hand that you cannot possibly learn from thinking about it, especially when it comes to like detailed tests, things like, sealing, complex vibe, complex aero. Some physics are way easier to be tested in reality than done analytically. Not always the case. It depends. Yes, we're getting better and better at modeling things as a species, but, categorize your risk into, is this something where I'm going to just have to test it to figure out if it works? Like the aging of a PSA tape in UV and humidity. There's, some PhD nerd in a university has like an equation for that or a model for that, and it's probably wrong. You don't have that equation or model. It's probably extremely specific to whatever they're studying, but you can study it empirically live, as opposed to basic structural analysis. Will my aluminum break under this load? That is something that we have hand calcs for, we have simulation for, we have tons of tools to answer that question. It's actually pretty easy to answer analytically, and you could actually get away with not testing that much or testing much later. So there's this kind of like test versus analysis maturity. Some domains and some problems very easy to analyze with high confidence. Don't worry about it. Some domains require testing, which means you have to have the parts, which means you have to have the parts early. So you want to avoid boondoggles. You want to have high speed of iteration. The problem is there's usually a dividing line between prototype process and production process. And in general, like here's the saying. If you know what you want and you want 1 million of them a year, someone is willing to take your money to make that thing as cheap as possible because it's a certain business. If you go to some company and say, I want 1 million of these widgets a year exactly like this, someone in the world will come up with some crazy tool that does it. And then, maybe it's just an injection molding tool that they cut for 20 grand. Maybe it's an exotic stamping press that has to be built. Maybe it's like a absolutely interesting custom design R&D new welding system that doesn't exist yet. Like humans are really good at solving those kind of problems. But if you know what you want, eventually you can get it for cheap because you're willing to pay people upfront fixed cost capex to make the variable cost low. If you don't know what you want, then it's going to be expensive. And that's basically the difference between prototype and production. Is I want 10 of these shapes because next week I might want 10 of a slightly different shape. You're not going to go set up a production line to build 1 million of those things because you don't think you want 1 million. That's okay. Prototype to production, though, is sometimes quite challenging because not every material, process, and geometry is available the same way in prototype and production. And that's the problem because early in the design stage, you want fast iteration to get it right. Later in the design stage, you want really cheap and pristine. It's always the same every single time. These are fundamentally at odds. Like in the beginning of the design phase, everything changes rapidly. If it's wrong, you need to fix it rapidly. In the end of manufacturing, the goal is to have no change at all. It's like we made 1 million parts and we measured this critical dimension and they were all within this really tight spec. So there's also a fundamental kind of psychological, philosophical difference between manufacturing engineers and design engineers. Design engineers love changing things to make it better. Manufacturing engineers don't want to change anything because that's how they make it stable. Some designs and domains easily translate from prototype to production, and you basically can keep paying someone incrementally more money, and the lead time goes up incrementally, and then the cost per unit goes down incrementally. That's a lovely place to be. So let's say machining. Like, you get a quick turn prototype machine in the US, it's like $1,000. Okay, you order higher volume, you get it machined overseas. Now it becomes $100. Okay, now you realize we're going to optimize the machining paths. We're going to buy the custom machine that's exactly the right size. And for this, we're going to have exactly the right tools, automatic, robotic, whatever. Now it gets $50. At every stage in the process, you can spend incremental money up front, fixed cost. You have to wait a little bit longer, incremental lead time, but then you can get a better outcome. But there's no huge breakpoints where it's like all of a sudden you just have to buy $1 million tool to enter the game. Likewise, in some sheet metal, maybe you can laser cut it and bend it on a sketchy jig, and then eventually you would stamp it and bend it in tooling. The geometry and the material and the process are actually like, you can get the same geometry and the same material with two different processes, one of which has low capex, high iteration time, one of which has high capex, low iteration time. And that's fine, because you can basically go from, okay, for the first 100 units, I'm going to laser cut this and have it bent on like a press brake by hand. And then when you're like, yeah, I'm ready for 10,000 units, you can have it be entirely done in progressive die stamping tools. You're not changing your design from prototype to production, but there's a pretty big wall there. There's like basically a big step from you're in prototype land to you're in production land. And you cross that wall with money and lead time when you're ready. And what does ready mean? At some point, your prototype tools are either too expensive, or they're like slightly not reliable enough or slightly not accurate enough that you need to hit rate. It could be that, wow, the prototype laser cut parts are great, but we can only make, 1,000 a day, and we just really need 2,000 a day. The only way to get there and rate is stamping, even if the laser cuts were cheap. Practically, rate and cost go hand in hand. If you can make the parts faster, they're probably cheaper. But then there's the worst part of this, which is your primary structure, which is if you want a complex carbon fiber part. Basically, there's no good way to prototype that. I mean, you can maybe make some sort of soft tool and lay it up, but there's some applications or some cast part or some, you have some sheet metal shape that can only be made with stamping. You have some carbon fiber part that can only be made with a hard tool with an exotic process. You have some basically really obscure geometry or complicated material, or I want a carbon fiber filled plastic that's not available in machining form. Or like maybe the process prevents you from using prototype methods. Then you're stuck in a world where you have to go straight from idea to production. And when I say production, I mean it's a high capex, long lead tool. That's a really hard place to be. Hopefully you can choose an architecture that takes you out of that region. Sometimes you can't. Sometimes you just have to bite that bullet. You have to eat those vegetables, and then you're stuck in the slow begets slow, cautious begets cautious land, and you have to be really, really careful to get it right. Zooming way out, if you're going to start a program, oftentimes it's very tempting to be like, wow, I want high performance and low cost. Therefore, I have to use fancy processes that are really good at scale. And then they have all these special rules and all these special design requirements. And every single part of your system becomes a long lead, high capex, high risk part. That is so scary as a place to be, because it basically means you don't know if you're right until you've spent, thousands or millions of dollars and you've waited, tens or more weeks. You can only play that game if you're really, really good. Basically, the chance of failure just goes up the more and more parts you have that fit in that bucket. Or it just means that you're not going to get it right the first time. You're going to pay for a second iteration. It's just going to be really expensive in money or time. So ideally in your program, you have a balance of, well, some of these things will show up fast and are easy. Some of these things are careful or worrisome boondoggles. And then you can balance your risk accordingly in terms of, well, maybe this main structure needs to be a fancy part. I'm going to work on that early. It's going to be molded. I'm going to de-risk with DFM with vendors early because I'm scared about it. But the other little widget next to it is actually a tiny machine part. Who cares? I can afford to be wrong. And this helps kind of segregate out what you should work on in order. Like from the organizational standpoint, you work on the cross-functional interfaces first. From an engineering standpoint, you work on the multidisciplinary problems first. If something is electrical, mechanical, thermal, that's going to be harder than if it's just thermal mechanical. That's going to be harder than if it's just mechanical. That's going to be harder than if it's just geometry packaging. But then when it comes to the supply chain side, everything gets ranked by like first by lead time, then by tooling costs. If you had a cheap tool, if it's like a $5,000 tool, but it's 8-week lead, okay, you could afford to be wrong and redo it later, but you're going to pay the price in the time domain. What that means is you might release your first idea. 2 weeks later, you buy another tool. 2 weeks later, you buy another tool. 2 weeks later, you buy another tool. Now your first part shows up. Oh no, it's okay, but we think we fixed most of that in the second version that showed up. If your tools are cheap but they're long lead, you can play that game of just buying a lot of options because you'd rather have multiple options that you kick off every single week than try to pray and get lucky once. If the tools are long lead and expensive, oh my god, you got to get it right the first time. If the tools are short lead and expensive, this is not common, but I guess prototypes. If you have a one really expensive prototype, you can get it in 2 weeks, but just like you just machined the whole thing and it's big and expensive, then you would do that, bring it in at low quantity, learn everything you can, and then go to the next iteration. You basically have to choose how many iterations you get. You probably only get 1 or 2 or 3 because the money's too high, but it means that, or you just, if you can afford it, you just earn that money, earn that lesson, but at least it's not lead time risk. So ranking and prioritizing things is different across these different domains. Organizationally, you focus on the interfaces. Technically, you focus on the domains. Supply chain, you focus on the lead time and the cost. Other types of risks. It's very common for people to hear about some new miracle material or some new miracle process. They hear the first order, like it's good at doing A and B and C. And they're like, wow, I need A and B and C. And every process has a thing it's good at. And you use it for those things, but every process has second order effects and drawbacks. And if you're really pushing a process to its limits, you spend all of your time worried about the second order effects and drawbacks. Like you're not worried about the first order, like sheet metal. Sheet metal is constant thickness. You can do 2D cuts. You can do 3D bends. If you're doing stamping, okay, great. You can do 3D shapes and elongation. You can actually stretch and draw and form. Sheet metal is so good at making a continuous material with curvature and 2D cut features. It's really hard for you to grow a little locator pin or boss out of a piece of sheet metal. Do you have to now weld some little thing on? Do you have to do a little press fit thing on? Do you have to glue another thing on? Like the sheet metal is really good at supporting 2D cuts. It's easy to bolt through. It's hard to bolt into unless it's thick enough it can support inserts and stuff. So, or wow, now that you have all these inserts, the inserts leak, or maybe the inserts are too close to the bend edge, and then all of a sudden there's a whole new category of design rules that show up that make your life complicated, and that's basically what dictates the size of your thing. I've worked on so many sheet metal parts where everything was great until we added the threaded insert, and then wow, the threaded insert is big, and then it has a minimum edge to center line distance, so it doesn't warp the material when you press it in, and then all of a sudden your part is twice as big as you thought it was going to be, and you can't tap that material because you needed to make some weird swoopy shapes. You used and it needs to be light. So you use a thin, soft material, but now you need a hard, strong thread locally. You can't tap it because it's too thin in 2 weeks. You have to use an insert, but now the insert gives you geometry challenges. Like that's the kind of situation where if you didn't know all the rules about sheet metal and sheet metal with inserts, you could fall in love with it, commit to designing it this way, get all the way through your design, and if you do DFM late, you might find only at the end, oh, I'm violating certain rules. It doesn't work like that. That's a huge problem. We are often tempted to use the processes we just learned about because we only heard the good things about them and we didn't hear the bad. I have been burned by this many times. I fell in love with the process. I'm going to do everything this way. You start making a few things, you learn the first pass design rules, and then you get wrecked in DFM when they're like, oh, actually, we can't do it that way. We can't do it in this order. We can't do it in that size. And all of a sudden, you're stuck. And you're thinking, man, my old process was actually not that bad. You have to be careful about choosing the process up front that gives you the geometry and material flexibility you need to solve the problem. For example, machining can do high geometric complexity, but you pay for it. Casting can do high geometric complexity cheaply, but you have bad material properties and you have difficulties in fatigue and structural soundness and leaking because the cast materials are just not as good as the wrought materials. Like they need to, and if you want to know why, it's like the aluminums that you make wrought are designed for forging and ingots and hammering. If you need to cast it, all of a sudden it needs to also be good to handle in a liquid state. It needs to be fluid. It needs to have a narrow melting region. Like by making it castable, the alloy has additional requirements, which basically make it worse at being strong. Also, the casting process has a really complex thermal like history, and you get grains and crystals in all different directions. You get porosity and voids and defects. Like when you open up the geometry lever, you usually sacrifice material. This is actually pretty true across the board. If you want to mold something really thin and big with complex features, all the molders would be like, hey, can you use polypropylene? Can you use like a low temp nylon, something that's really low temperature, easy to inject, low viscosity? But then if you're in aerospace, you'd be like, I actually need a high temp glass filled fancy polymer, and it's really hard to inject, and the molds are more expensive and it wears out faster. So there's a trade-off between geometry and properties, always. And so if you choose the wrong process, you're going to end up in a situation where I can't get the properties of the geometry that I want at the same time without adding more complexity. And so it's very important when you're choosing a new process to learn about the first order effects. Sheet metal, constant thickness, bends and 2D cuts, it's great. Injection molding, constant thickness, you have to have drafts and angles, and then you get wrecked on like gating and fill and stuff. You have to learn the first order and the second order before you can feel confident that it's actually going to work for you. Get to DFM early. Don't fall in love in a vacuum with a new process, because it always looks good on paper. If you go read some article about 3D printing is great, like it'll tell you all the good things about 3D printing. They're not going to tell you the bad things. They want to sell you a product. They want your money. But when you go into the details, like, oh, well, when I 3D print this part, it's going to be anisotropic, and it's going to be better in these directions than those directions, and it might not be leak-free, and I might need to do these post-processing steps, and all of a sudden, this geometry easy and that geometry hard. You can't have an enclosed shape. It needs to have, holes for the powder to come out. Like, those are the rules that actually make your design possible or not. You have to be intimately familiar with the capabilities of the process before you can choose it, to make sure that architecturally, if you choose this material and geometry and process, it's going to be flexible enough to cover for future changes, because change is always going to happen in a program. There's always going to be more of it. Whatever you want today, it's going to be different in a week. It's going to be different in a month. If your architecture is good, you can add incremental detail and incremental small requirements without blowing up the architecture, without having architectural churn and burn, without having a boondoggle. It's like, oh, I have a machine part and I need to add one more hole. Not a big deal. That's basically no tooling cost. Okay, maybe there's a programming fee or a setup fee. It might be like a few $100. And all of a sudden, it's short lead. In a few weeks, you can get parts with a new hole in it. Great. Well, I want the hole to be slightly bigger. Awesome. Easy. As you go to something that's more tooled, maybe casting, it becomes harder to put that new hole in. Well, maybe if you cast a blob of metal, you could then re-drill it later. So if you planned ahead and you had extra features that you can then post-machine, you've bought yourself insurance for future changes. But if you didn't, now you got to go make a casting tool change, which can be done. It costs money, it costs time. You can then add more metal and you can go drill a hole into it. So sometimes there's a way for you to buy insurance. And that's like maybe in the tool, you tell the vendor, these areas are highly likely to change. Please make them an insert. Those areas are very precise, not likely to change. You don't need an insert there. Planning ahead for future issues. Like if you cast some part and you have a hole drilled right next to the edge, and then later you need a bigger bolt. This is like the classic aerospace problem is I have two things that bolt together and they're going to fail at the bolts because interfaces are usually weaker than their structure. And then the loads go up. Okay, the loads doubled because someone made a mistake in the other department. Screw those people. Now, what do? Well, I don't have room to put in bigger bolts because I put my bolts right next to the edge. Geez. So and then you have to go buy really fancy bolts, and then you have really fancy bolts that are really strong, and you tighten them really hard, and all of a sudden it's yielding your surfaces because your surfaces are some weak casting. You can easily get into a boondoggle where you have expensive bolts and you're like, have to go machine prototypes out of fancier materials because things didn't work out. If you know that that's a possibility, here's what you do. You look at that joint, you size it for what you need to be, but you leave enough room around the holes so that even if the loads doubled later, you'd still have enough material to drill it out, put in a larger bolt, maintain your your edge to center distance, your E over D, and then you're okay. And that requires forethought and wisdom and experience. You have to basically you have to look into the future, you have to take your crystal ball, you have to look at it, and you say, what are the bad things that might happen to me in the future? And how do I put myself in a really good position to avoid them? And sometimes you can buy really cheap insurance up front that covers for a wide range of catastrophes. And you walk away looking like a hero because someone in the other department made some mistake, they always do, that doubled the loads. And you're like, don't worry, I got you. I'm going to drill them out to a different size. That's just a post-machining change. I'm going to upgrade to the next bolt. That's also a standard part. I'm not buying exotic space bolts that are impossible to source. And then you're not the problem. You're not the boondoggle. It's someone else's interface who is really flying too close to the sun. That's going to have to go redesign their entire part because load's doubled. Like, good architecture is flexible. It accommodates change. It gives you a wide range of detailed design work to play in. And it's easy to accommodate those small changes without breaking. A bad architecture is one that just barely meets current requirements, and if you want to do anything slightly different, the whole thing blows up, and then you're stuck churning through, I'm going to use material A and process B, and then you're all of a sudden, I'm going to use material C and process D, then all of a sudden, like, it goes from a casting to a sheet metal to an impact extrusion to a carbon fiber to a plastic, and then you just run in this circle about you have to explore all the different processes, and you just burn up tons and tons and tons of time. Be wise about the capabilities and the drawbacks of your process to make sure they're architecturally flexible enough to handle reasonable expected changes. It is reasonable to expect that loads will go up. I've never been in a program where loads kept going down. Or if they kept going down, guess what? No one worried about it. No one talked about it. It didn't matter. When loads go up and things break, people care. It matters. So risk assessment. There's kind of like a tier here. If you're making a bracket, and the bracket has to do two things. One, geometrically, it needs to hold A to B. It needs to be in the right place, be the right size. And then two, mechanically, it needs to be strong enough and stiff enough to do the bracketry that it needs to do. There's a reason why people give brackets to junior engineers. It's a pretty easy thing to do. Because the amount of requirements are low, the design space is large, and therefore there's many possible solutions. This is like a high entropy set. Like, you have these two variables, and imagine if the x-axis is geometry and the y-axis is mechanical strength. You could draw a huge circle of reasonable implementations. Okay, now we're going to add a third requirement, which is the bracket has to be thermally conductive because we're in some spacecraft and this is a conduction path or something. All of a sudden, that 2D space with a circle drawn in it becomes a 3D space with some sort of like sphere or curve living in it of acceptable design solutions. By adding another domain, thermals, we actually take a huge cut out of all the possible implementations because maybe your best structural steel or stainless or whatever has really terrible thermal properties. And now you have to look at some exotic aluminum alloy or exotic copper alloy or molybdenum or tungsten. Like, by adding a new domain of requirements, that has a huge impact on the available materials, processes, and methods. Like, maybe it used to be just a piece of bent steel sheet metal, but now if it needs to be more conductive, it actually needs to be a sawn-off part of an aluminum extrusion with post-machining. Like, now the options available to you have gone down and the requirements have gone up. Okay, now let's say the bracket needs to be thermally conductive and electrically insulating. Now we've added a fourth domain. Oh my goodness, this is really hard because, nature doesn't give us that many materials that do that. And you get into this situation where solving any 2 out of 3 or any 3 out of 4 requirements is very easy, but getting all of them is really hard. So now you're in a situation where, well, I could make it out of ceramic, and it would be electrically insulating and, depending on ceramic, thermally conductive, but it'd be expensive and very brittle. You could make it out of, plastic. It'd be electrically insulating. It'd be an easy geometry. Depending on the plastic, it might be strong enough, but it won't be thermally conductive enough. Unless you start buying exotic thermally conductive plastics, which are just not that good. You could make it out of, a really fancy copper alloy where like high conductivity, high strength, and good geometry. It's expensive. But now how do you insulate? Okay, well now maybe we need to powder coat it, or we need to put on insulating sheets, or we need to add another part or a feature or a coating. And these are where things get really interesting in terms of when you have multiple domains, they tend to have countervailing requirements where it's easy to solve some but not the others. And this is where the number of options available starts to really dwindle, and they all start to look very different from each other. That's a scary place to be because now, if you think you're going to choose copper plus powder coat, and you go really far in that design, and then you get the DFM, and you're like, well, it turns out, okay, we're going to bolt into this thing, and we're bolting into it. It doesn't matter if it's powder coated, the bolt's going to be conductive. We don't want to use, ceramic or plastic bolts. All of a sudden, it becomes really hard to achieve the electrical insulation properties. So we're going to abandon that design that we put all this work into and go way back to a conductive plastic. Okay, and then we look at all the data sheets for conductive plastics, and the best conductivity is 3 or 4 watt per meter Kelvin or something, and it's ceramic filled, it's brittle, and that's just not going to work mechanically. And then this is where you get into architectural churn, where in an attempt to meet all these countervailing requirements, with imperfect knowledge of the processes and materials available, you choose one, explore it in depth, which is expensive, realize late it's not going to work, then go to a completely different design, different material, different geometry, different process, different trade-offs, explore that one in detail. You might end up learning, it's a great learning exercise. You can get like your PhD in materials. Like, you might explore 4 or 5 completely different designs that all don't work for different reasons. That is a scary place to be. Those are hard problems to solve because there's multiple domains. Basically, a problem gets harder when you add more domains of requirements, as well as when the requirements within those domains go up. If the bracket needs to be located within a millimeter, and it needs to have 10 megapascals of stress, and it needs to be 1 watt per meter Kelvin, and it needs to have vague insulation properties. Okay, there's a lot of domains, but the amount we're asking for in every domain is actually pretty low. It's fine. When you have a lot of domains, and the amount you're asking for in every domain is really high, that's when things get even harder, where it's like, well, I need it to be located within a micron, and I need it to be carrying 100 or 1,000 megapascal stresses, and I need a conductivity above 200, and I need electrical insulation. And it has to operate at high temperature. Now you're like, okay, exotic ceramics, or, exotic metals with coatings, or the amount of options go down, which means the amount of work you have to do goes up, and the chance that you get screwed by requirements goes up. It turns into a boondoggle. How do you avoid this? Well, ideally, one is you just get really good and you just know the answers to these problems, and you just happen to know the miracle material and the process that solves it, and then you use it, and maybe you just found it. Like, okay, maybe the answer was high strength copper plus coating, special coating engineering, ceramic bushings. Awesome, we're good to go. Not everyone is capable of finding that solution, and a younger, more junior engineer that doesn't have a huge toolbox of materials and geometry and process might not come up with an elegant design. However, usually what you can do is you can find a design that's kind of gross by chopping it up into multiple parts, and each of those parts has fewer requirements. So this is, if you have to move really fast and solve a hard problem, your goal is to minimize the amount of domains in every part, and you're going to chop up a problem into multiple parts that each have small numbers of requirements. That's the, I'm going to have my structural thing, and I'm going to put my insulation thing on it, and then I'm going to make sure that both those are good at high temp. You've chopped up the electrically insulating and the thermally conductive requirements separately. Now, if you're a more experienced engineer and you need to get a higher performance, then you really actually just do need to solve the problem all at once, which is tricky. It's hard. It might take a few tries. You might have to try multiple options. And also that usually at high volume, long term, you want a highly integrated design that meets all requirements at once in just one part, with just one material, just one process. It'll be easier to make that way long term. For a prototype to get off the ground, you might need to make it really complicated and have 3 or 4 pieces that all come together to do the work. It's not going to be as elegant, it's not going to be as cost effective, but it's easier psychologically to make that happen. So if you're ranking a problem, you might rank it by the number of domains and how scary those domains are. For example, is this like traditional undergrad level analysis required to make this part work? Or is this like maybe industry standard complex analysis or just like world-class research. If you're trying to design a rocket engine and, you know, do you need to do breakthrough physics in combustible liquid mixing at high temperatures and hypersonic velocities to answer this question? Or can you just read a book from the 50s about rocket engines? You know, those are two different levels of problems to solve. So the worst thing you can do is I have a I have an interface with many departments. I have long lead high capex tooling, and I have many domains, and in every domain I'm pushing the requirements and limits. That's when things get big, expensive, and slow. And traditionally that is aerospace and like military, where it turns out that this problem is just really, really, really hard. And we will go invent new materials and new processes to do it. Like, I want to forge an entire aircraft out of titanium in one step. It turns out there's only one machine in the entire country, the 50 at Alcoa, that can do that. And then I'm going to go have an entire research team figuring out how to make my, titanium plate near net forging work so I can make the F-35. You're talking like a 5 or 10 or 15-year program to go develop that set of technologies. This is now big science. Like, if your company is, titanium forging heavy industries, awesome. That's the kind of problem you want to solve. If you're a small startup or a medium-sized company, you cannot afford that confluence of problems. You don't have the money, you don't have the time, you don't have the expertise, you don't have the deep research nerds who can come up with new alloys and new processes to make it happen. That's like big government, big science kind of stuff. A lot of products are frankly easier than that. And mostly the goal is timeline pressure and cost pressure, which is we're making something that is well within the capability of humans to make, but the details of what we're doing are a little bit tricky and new. Please go solve the details for me. And if you can convert a really big, scary, hard problem into a series of easier problems, you're going to have a better time. So if you had to rank problems, you can rank them by number of domains, difficulty within each domain. Is it high cost? Is it long lead time? Are there many vendors that can do it? Are there few vendors that can do it? And then separately, there could be a design that only has a few domains. Let's say it's really just an electrical, thermal, mechanical problem, and you have a really good mechanical and electrical team, but you just don't have any thermal skills. Guess where it's going to fail? It's going to fail in the thermal domain. It's not going to fail in the mechanical and electrical domain. So ironically, here's the kicker. If you're good at A and B, but the problem requires A, B, and C, you should spend all of your time and effort working on C, because you're probably good enough to make A and B happen at the last minute in a short amount of time, because that's what you're familiar with. This is very counterintuitive, and it bothers people, because when they encounter a problem that's A and B and C, they're like, wow, I'm so good at A and B, I'm going to optimize that to death, and I guess C will probably happen. And then later they realize, wow, there was actually a stakeholder that really cared about C, and there was a really big, scary requirement related to C, and we didn't get that requirement figured out on time, and I designed the perfect architecture for A and B, and it's high performance and it's lovely, and it just doesn't work for C at all. And now I have to throw it all out and start again. And that makes people upset. It makes people think that there's bad leadership, there's bad program management, there's this, the other department screwed me. Truthfully, if it's your part, you own it. If you miss constraint C and you optimize the hell out of A and B at the expense of C, that's on you. You want to avoid this. So you have to seek out the uncertainty and doubt of, okay, this is new to me. What should I be worried about in what order? I should be worried about the things I don't know and I don't understand more than the ones that I do know and do understand. Because I know I can get myself out of a pinch in a thermal mechanical world faster than I can in an electrical aero world. I just, know more about those things. So you have to understand, does the shape of your skill set match the shape of the problem? If it doesn't, you should be worried about the things you're not good at, spend more time upfront on those, seek out expertise and advice in those areas, because that's the area you're most likely to fail. Now, if you know the problem has a few domains and you're good at all those domains and the requirements are low, you can probably comfortably say that that's an easy problem and you can do it later. And you should prioritize something else. I've always been bothered by when people say, oh, how did you know to do this? And say, oh, I just have experience. Like, ask myself, well, what does experience mean? And here's a few attempts. Experience is The difference between someone with experience and without is the person with experience will solve the same problems in the right order. When I say right order, it means the order that causes the least amount of shenanigans and disruption in terms of if you solve A, then B, then C, then D, the design space slowly, beautifully converges to the right answer, and you never had architectural churn, and it was always pretty clear what was going on, and basically at every point in the design, it was correct, but just vague, and then it became correct and precise. And it was always a good answer, but just kind of uncertain, and the certainty went up over time. That's what experience gives you. Someone unexperienced, if you look at the progress of the program, it's like we're going full to the right, now we're going full to the left, now we're going up, now we're going down, now we're going sideways. And eventually, after hunting through many things, they found something, they did that beautiful convergence, and maybe ended up okay or not that great. So experience is solving the problem in the right order such that you minimize the chance of architectural churn. Basically, it comes to, do you know what the hard parts of the problem are going to be, and did you solve those first? Like in the bracket design, wow, I need this bracket to be like thermal conductivity 200 watt per meter Kelvin or above. It turns out that requirement is going to basically be architecturally defining. I could write down only like maybe 5 materials that get me there. It's like aluminum, copper, silver, just a few ceramics. There's not many options there. So all of a sudden, if you're looking at this high dimensional design space, maybe the structural is very easy and the electrical is very easy and the geometry is very easy, but the thermal requirement is this very narrow region that you have to live in. You have to go solve that first, understand that problem first, and then make the other requirement solve. Again, if you do it in the other way, which is, well, I'm really good at electrical, mechanical, and geometry, I'm going to go solve those problems, and I just hope that the thermals will work out later. That's when you get yourself into trouble because you didn't realize how narrow the design space was in that other domain, and then you got wrecked. And then you had to blow up your architecture, then you had to try again, then you ended up with some high fixed cost, long lead CapEx process that only one company can do. And then everyone hates you because you screwed up. So the experience is recognizing that some domains are harder than others because of your skill set. Some requirements are harder than others because they're pushing more towards theoretical physical limits than others. And then solving those problems first. And that's why it comes from experience, because if you have a bigger toolbox, if you know about more materials, you know about more processes, you know about more geometry tricks, you have a better chance of recognizing when a certain requirement in a certain domain is either really hard or really easy. And then you can plan for it accordingly. And then you focus on the things that are difficult and new to you, as opposed to ignoring them. And then you slowly converge on the ones that are easier. It comes from experience because people aren't born knowing all the materials, all the processes, all the geometry tricks in the book. And some of those things are either slow and expensive to learn. Like you might have had to build 10 things to learn about these processes, or you might just have to have the right book, or have to know the right person, or you had the right conversation with your colleague in the hallway, and then you got that information, or you smash your head against cold hard reality. So this is, if you're doing everything from first principles and you're really smart, but you don't have much experience, you're gonna hit a lot of potholes in the road. And you can fix it, but it just takes time and money. If you're more experienced and you have a bigger toolbox, this is what I call second principles. First principles physics is, these are true statements about the world. These are our models. These are our laws. These are our codified observations from science. Independent of what humans do, they are true. Second principles, this is basically human industry, human engineering. Like the fact that you can buy a bolt that has a socket head and it's M4 by 0.7, that's second principles. Like physics allows you to make a bolt of any size, of any thread pitch, of almost any material, and the physics is still the same. But the fact that an M4 by 0.7 is a standard bolt available in 20 millimeters out of stainless steel, that's second principles. If you had to engineer fasteners from the ground up, first principles, you could do it. It just takes a lot of time. And then you'd learn all the details that the bolt industry learned. They learned everything about thread pitch. They learned everything about the radius of the root of the thread and fatigue. They learned about torque and tightening and lubrication and torque tools and torque versus angle and how to design different heads for wrenches and sockets. It's like, those are all second principle details. It's how big your toolbox is. Again, physics allows you to make ceramic bolts. And there's a few companies that will sell you ceramic bolts. There's not many people using ceramic bolts for a reason, but there's a huge amount of bolts made out of other materials. That's something you should know about. It's a thing you should use to your advantage. So the bigger your toolbox is, which comes from experience and time, because you can teach someone first principles. You can teach a smart high school kid first principles physics, sizing, analysis, and engineering, but they aren't going to learn about what bolts are available until they go try to build something. And that's a rate-limited process where you acquire experience by smashing your head against reality. So don't forget second principles. Boondoggles. You don't want to be a boondoggle. Usually it's because you underestimated the problem. You got wrong requirements. Detailed design. Sometimes you have a beautiful architecture and then it gets hung up in one area. We're like, wow, it's actually perfect, except we thought this was going to be okay. We had some late breaking news on DFM, and all of a sudden, this one area just doesn't work. And then things become really tricky, but the rest of the architecture is good. That's just like a difficult position to be in. Hopefully you don't have to be there. Again, you can avoid that by getting DFM early, worrying about interfaces early, all that jazz. Interfaces. Where do things break? Things break at the edges, the ends, the bolts, the clips, the springs. They don't break in the middle. People in general, interfaces are complicated because there's usually a rapid change in geometry and material. The load cases or boundary conditions are strange. So if you had to design a block with holes in it, you should spend most of your time worried about the holes on the block. Because if you got the block size wrong and it ripped itself in half, you could probably just add more material without affecting other parts or people. It's pretty rare that a big just net section fails. It's very, very, very common for a welded joint to fail because there was some porosity or some inclusions or bad metallurgy or a weird cooling rate or hydrogen embrittlement. It's very easy for a bolt to fail because it was slightly the wrong geometry, or it wasn't lubricated, or it wasn't tightened, or it wasn't inspected, or it corroded, or there was whatever. Like, whenever you have high geometric complexity, which happens in joints, or high material complexity, like things are in the different part of the galvanic series, things are of different CTEs, things have different thermal conductivities, you're just opening yourself up for a bunch of new challenges to show up. Basically, the entropy goes up. Like, the amount of things that can go wrong is higher because the amount of different things in one area is really high. When you put this all together, like, some of the hardest things that there are like electrical connectors. Because mechanically, you got to get these two-piece metals to touch. And then electrically, they have to have low resistance. And then thermally, they need to not overheat. And then there's like a tolerance loop. And there's a data strategy. And then from a material standpoint, you have to be worried about vibe. You got to be worried about thermals. You got to be worried about electrical isolation and conductivity. And from a material standpoint, there's like corrosion and galvanic compatibility and ingress. It's like you have to do all these things at the same time in the same place. And there's tons of countervailing requirements. And a lot of it has to be tested. So testing versus analysis. Again, if you can size your part by doing sigma equals F over A, awesome. If you can size it with FEA, still easy. If you have to do a really bespoke test, okay, it's going to be harder for you to learn about the problem. Seals. Seals are really hard for this reason in terms of, at the end, you're going to have to test the seal. It's a complex interaction of multiple materials, like an O-ring seal. Even though we have the Parker O-ring handbook, and you can basically buy a standard thing and use standard rules of thumb, second principles to get it right, it's a piece of debris might cut through it, or maybe someone was handling it wrong, or maybe it touched some sharp thread, or maybe you didn't look at the full chemical compatibility chart and there's some oil that slowly caused it to absorb over time. Some things are trickier than they look, and you should just be aware of an electrical connector or an O-ring seal. It's actually a very complex piece of physics. Lots of material, lots of geometry, lots of shenanigans are going on there. Don't underestimate it. In general, you want to proceed from, in the very beginning, you have stakeholders. Like, okay, who cares? Then there's requirements. What do they want? And ideally, this is just true and absolute. Imagine you had no idea what the part was going to look like, or even if there was a part at all. But you had people who wanted things. And it can be described quantitatively, like this part must survive 10 Gs of acceleration at 10 Hertz. It also must have the ability to dissipate 1 watt to ambient thermally. It also must have this electrical connection. It also must do this other thing mechanically, you know? Ideally, you have a full specification of what it must do and what success looks like that's completely independent of a possible implementation. You don't want to be like, the pins need to be 2 millimeters to be strong enough. That's not a good requirement. The requirement is locational accuracy must be better than X and strength must be higher than Y. Maybe use pins, maybe use bolts, maybe use glue, maybe use a kinematic coupling, maybe use precision alignment with a magnetic levitated whatever and UV cure glue. There's a million different ways to attach things. Just write the requirements for what it has to do without specifying the implementation. Okay, so then you have architecture. Architecture is when you're choosing what demons you want to fight. You're evaluating the requirements against the domains and the difficulty in those domains, and you're choosing a I think I can make this out of 2 pieces. Piece 1 takes requirements A and B. Piece 2 takes requirements C and D. I'm going to consider these materials and these processes for piece 1 and piece 2. And I know that that's going to cover all the range of possible requirements. A bad architecture would be like, yep, I think this is one part, and I'm just going to use the material and process that I know best, even though it clearly doesn't meet requirements C and D. So the architecture stage is usually kind of hard to define of what's the difference between architecture and design. It's usually you're choosing part split, you're choosing material, process, and geometry. And if you make the right choice there, everything smoothly converges after that. All right, but then initial sizing. Initial sizing is when you're asking yourself, it's like, hey, design brakes for my scooter. Okay, so are these going to look like the brakes on a car, or are they going to look like the brakes on a bicycle, or are they going to look like, let's say scooters didn't exist, and someone had this new idea for a human-powered electric vehicle e-mobility thing. Okay, it probably looks a little bit like a bicycle, but maybe smaller. But it's definitely not like a car. Okay, what are the first principles of physics that go into it? And the architecture would be, I am going to use a friction on a disc to provide braking torque. The other architectures would be like, I'm going to use regen braking on a motor, or I'm going to, shove a stick into the ground, or use a parachute. Those are other architectures for braking. One architecture would be, I'm going to do friction on a disc. So the initial sizing is, okay, well, what are the key loads? What are the key limitations? And this is where you get a rough idea of, I'm probably not going to use a 2-meter diameter, 100 micron foil as my braking disc. It probably needs to be like 200 millimeters in diameter and maybe 1 millimeter thick, because I have stress calcs that show I can get the torque I need at this radius, and I have these reasonable stresses, and it has that reasonable temperature, and it has this kind of thermal. Like, the goal of the initial sizing is from 10 feet away, it's going to look correct, like the final design. And all of your key dimensions are correct within maybe 20-30% of, and you've captured all the domains. It's like, here's the friction, here's the torque, here's the heating, here's the thermals. I'm going to make this out of a piece of stamped stainless, and I'm going to deburr it. And I know that, okay, the stainless isn't that thermally conductive, but it has really high strength and high temp, and I'm going to use these brake pads, and I have sized the actuators to make the force, to make the friction, to make the torque. That's initial sizing. Initial sizing is usually enough for you to feel like, okay, this is possible, and it would look like this. And then you can start doing detail design. Detail design is, okay, well, how much does it weigh? And how much does it cost? And where do the bolts go? And is the radius 1 millimeter or 2 millimeters? And am I going to make it out of, aluminum alloy 1 or aluminum alloy 2? Like, really kind of nitty gritty details where the certainty is now within 5 or 10%. And you're doing a lot of CAD, you're doing a lot of drawings, you're doing a lot of prototypes. If it's usually pretty good to build something right after you do initial sizing. If you have enough initial sizing to convince yourself it's correct, you can probably go build it, or you can go analyze it, optimize it to death. In general, if you are limited by time, it's better to do initial sizing, build one, test everything about it, then go build, because you're going to figure out what's wrong with your model. And then it's very tempting to be like, I did initial sizing, it's roughly this big. Now I'm going to take 2 weeks to write a big MATLAB script, and I'm going to sweep every possible variable, and I'm going to come up with the perfect break. And you're actually just missing something, like, it turns out that your stainless is going to get too hot, or you didn't drill any holes in the brake rotor, so the gases that evolved from the surface when the oil boils off are going to cause your pads to flow, and you really just needed some little holes or ripples in the surface to take that gas out. That's something you're not going to find out in your model unless your model is just like heroically smart, which is very unlikely. You're going to find that out in real life. Oh, I was braking really hard and I boiled my brake fluid because my brake fluid wasn't high enough temp. That's a second principle thing related to what brake fluids you can buy. Like I've had this happen to me. We were racing the race car. We braked really hard multiple times in a row. All of a sudden they get really spongy. What's going on? Oh, we were using .3 instead of .4 or .5 brake fluid. That's something that your model, if you're smart, your model might tell you the brake fluid temperature. But unless you know why that's important or not, you're not going to act on it. So go build it, learn from it, learn what's wrong, and then it's a lot easier to invest in a big model later. One of the big themes here is invest proportional to maturity. If you have a hand sketch, maybe you should go spend a few $100 making a prototype. You're probably not going to spend a few $1 million on tooling. If you have several functioning prototypes and a model that predicts behavior, cool. Maybe you should go spend a few tens of thousands of dollars on prototypes and tooling to make it even better. Like first you make 1, then you make 10, then you make 100, then you make 1,000, then you make 10,000. Like in order, and every time you 10x the volume, it's going to look different. It's going to get better. If you show me the volume, I'll show you the processes and the level of analysis behind it. Where things get really hard is where you need quantity one perfect object to exist. And that's when you get into big boondoggle aerospace stuff where it's, I just need one space shuttle primary structure. It's, wow, that's a really hard thing to make. It turns out if you're making scooters, it's a lot easier. So you don't want to, if you invest ahead of maturity, you might end up throwing away a lot of money. If you invest behind maturity, it means that you're probably dragging bad prototype ideas into the future and paying for it with like low reliability or high cost. Thank you so much for listening to this episode of Precision Stuff. This is a little bit different from what we usually do. I hope this was a helpful story and it communicated some of the risks that happen in the real world engineering environment. If you'd like to hear more about this, let me know. Thank you so much.